In the second of our exploration of pointers, we're going to have a look at a bit of a mixed bag of different aspects surrounding the use of pointers. We have a little bit of reminder. I mean, pointers are an integral part, certainly to C, to C++. They give us the ability to have a good amount of control over how we access data and refer to data within our programs. So going through it, as mentioned, but we'll have a few slides on a wide range of different topics. There isn't sort of any sort of grand sweep to this in terms of building of things, so it's going to be sort of jumping from one topic to another. Start off with an item highlighting some of the dangers of pointers. So whenever we create a pointer, to be more precise, a pointer variable, we will be reserving a bit of memory that will hold an address, and we can specify what we want to point to. Now, in line 1 here, we're creating an integer pointer, so something that points to an int. It's created same as any other variable, like int a or whatever, but it will not have an assigned value, which is to say that we will not have assigned it a value at that point of definition. However, there will be some value in whatever bytes are yet to be allocated for it. And we could, if we wanted to, but we shouldn't, in line 2, we could then make immediate use of that pointer. So we're saying okay, so pointer to somewhere, there'll be some address. We want to go to that address and we want to set it to 0. Now that's corrupting memory. We're changing a piece of memory, but we have no idea what piece of memory that we are changing. Obviously, it's a silly thing to do. You would never do it purposefully, but sometimes when bugs introduced into programs, you might inadvertently do something similar to this, particularly if you have a pointer variable and for whatever reason it doesn't get to be assigned to something or linked up with something. Then there's a risk that may be not noticed and that pointer variable may be used. The reasons these things are so nasty are that the content of the memory that's set aside for the pointer variable may change from one run of the program to the next. Depending on where that is, you may change something and there'll be no noticeable effect, or it may change a critical piece of the program that should result in an immediate crash. So it's the type of thing that can lead to just random crashes of a program. Very, very hard to track down where that type of bug actually comes from. So we need to be careful anytime we're using pointers. Slide here in terms of what's known as the arrow operator, and it's a useful way of dereferencing a pointer, of going and accessing the thing that we point to, particularly used with structs. So give you an illustration over here. A small fragment of code on the far left hand side. We're creating a rectangle struct that has some int val inside it, and just next to that we've got 3 different ways, all equivalent in terms of functionality, of accessing the val int within the struct and assigning equal to a value, 20 in this case. So in line 1 we're creating our new rectangle structure. So if this is inside a method, it'll be allocating some memory then on the stack where we can do that. And we're using the dot operator then to go to a rectangle structure to access the val member or property within it and to set that integer equal to value of 20. So that's nice and clean in the way it would be used. In line 4, we're creating another rectangle. We're using the new keyword here. So in this case, it's something that gets to be created on the heap. So we're allocating some memory in the heap, sufficient to hold a rectangle, allocating and setting aside for that purpose. The new keyword is giving us back a pointer to the bit of new memory that we allocated, and then we've got our rec pointer, ptr rec. At line 5, inside the brackets, we're dereferencing that pointer. So we're saying, okay, we're pointing to a rectangle. I want to dereference it. I want to access the actual rec structure that I'm pointing to. And then I'm using the dot operator and then going to the val and setting it equal to 20. Now, again, exact same function. The 2 different forms come in here, and the one lives on our stack, one lives in the heap, and we're accessing them slightly differently. Line 5 looks a little bit cumbersome, I suppose. And the arrow operator was put in as a way of providing a more straightforward, easy, nice, elegant way of accessing particular structure type data through, or classes, through pointers. So again, line 7, we're creating exact same way of creating it. So it resides on the heap, get a pointer to it. And in line 8 down at the bottom, there we're using our arrow operator. And effectively that's interpreted to say as dereference, access the thing that the pointer points to, and then it's going to have a property called val, access that, and in this case set it equal to be 20. So you'll probably see that of use, but it's a convenient way of getting access to these things. So a little bit about pointer arithmetic. So when we think about an address, it's going to be a numerical address. You could look at it and go, well, that's just an integer. Now, remember back to when we looked at data types, when we talked about a data type, we said there was two core components to it. One was a list of acceptable, permissible values. And then alongside that, we had a set of operations that we could apply to those values. So in terms of set of valid values, if we have an unsigned integer, the values that are permissible for this will be the same as the values that are permissible for the actual memory address itself. For pointer arithmetic then, if you think about a pointer, we do have a set of permissible operations that can be applied to them. So for example, it doesn't make sense to divide one pointer by another, but it can make sense to take a pointer and to add a number to it to either increment or decrement the particular address that you're referring to within memory. So you can see in this slide here that in terms of positive numerical values, so if you like an unsigned integer, the same values are there. For the operations, we can add or subtract a number to a pointer, we can increment, decrement it. That's basically changing, stepping the pointer forward and back within memory. And we can also compare two pointers to ask, are they pointing to the same address? Is one pointing to an address that is notionally higher or lower in terms of memory? And those operations are useful, and they're ones that we can then draw upon as part of our development and our programming. So you can see an example of it here. Now, this gets into the point that if you have a look at the illustration of code at the top, where in line 1 we are creating, or we've got an array of ints, presumably, and we're creating an integer pointer, and we're setting that equal to the address of the start of that array, the first element in the array. At line 2, we're adding 3 to that pointer. Now, that raises a question of, well, you're adding 3 to what? Is it the memory address that you have? So you go 3 bytes along? That isn't what happens. If you add 3 to an integer pointer, you step 3 integers along inside memory. So that if an integer is represented using 4 bytes, you'll jump forward 12 bytes within memory. So this is good. Incrementing and decrementing pointers, the step size is the size of the thing that the pointer points to in terms of the number of bytes that each individual entity reserves. That makes it easy then, given a pointer to a certain type, to jump forward 5 instances or jump back 2 instances in terms of moving through different types of data structures. And that's one of the strengths then of using pointers. You can see down at the bottom of the screen a few sort of common ways where we are either combining a post or a pre-increment with the dereferencing operation. So for example, on line 1, and this is where the precedents by which things get to be triggered come in. So we have a post increment that is a low precedence, so what we'll do at the very end. We have the dereferencing, so we'll dereference the pointer, use the int, and then increment the pointer by 1 step onto the next one. In line 2, we have a pre-increment. That is a high precedence, we'll do that one first. Then we will dereference, so we jump forward to the next int and actually use that value. Line 3 and 4 is the same notions, but there we're decrementing the value, stepping back. So they're short, convenient ways of saying use the pointer and then step to the next one, or step to the next one and use the pointer. Have to be careful, and this is fundamentally important. In C++, a pointer is just a pointer to location inside memory. If we're pointing to an array will have a start address, it'll also have an end address depending upon the size of it. In C++, the language assumes that it's up to the programmer. The programmer will take care not to step outside, for example, the array through which they're stepping. So if I have an array of 10 integers and I try to access array element 12, so notionally it's outside of it, C++ will let me do that. It'll say, sure, you want to do it, you must know what you're doing, you can go and access array position 12. So outside of the array, you'll have no idea what type of memory you're accessing, probably, and fundamentally dangerous. So we have to be careful if we are using pointer arithmetic, changing the thing that we point to, that we are bounded, that we do not inadvertently or accidentally step outside the data structure that is available, because that will lead to problems. Pointers and arrays then. So let's have a little look at how arrays and pointers are very, very closely linked. And they are in terms of their implementation, and in C++, it makes this linkage sort of interchangeable. Similar slide to one we had in the earlier one. This talks about how do you find an index within an array. If you have an array of 10,000 integers and you want to access position 5,341, how do you calculate location of 5,341? And going through thinking about this, you can't really have a lookup table, and introduces similar types of problems, but we can use simple arithmetic to do this by having the start location within memory, knowing the size of each of the elements, presuming they're the same, multiplying that by the index, and then adding that onto the start, and we then calculate the location in memory that corresponds to that particular sought index. You see an example then down at the bottom where start of the elements, we're adding on I, where this is the index, from 0 up till the size -1 times the size of the element. So we can jump through. So if we're doing an array lookup, in essence what we're doing is a little bit of pointer arithmetic. That's how arrays work under the surface. And in C++, you can use either of these forms of expressions, that they are somewhat interchangeable. So you can have an example here. Line 1, we're declaring an array of 10 integers called data. In line 2, we're creating a pointer that points to the address of the 0th element within that array. Down at line 4, we're just doing our normal, conventional lookup. And in line 5, we're doing exactly the same thing, but expressed using pointer arithmetic. And in essence, line 4 gets turned into line 5. That's how it works. So we go to our pointer at the start of the array, we add on to that the index, which jumps it forward by the appropriate number of in this case, integer-sized chunks, and we then dereference it. We look up the value. So line 4 and line 5 are functionally equivalent. And in fact, line 4 looks cleaner to us, that's what we're more inclined to use, but how it gets to be implemented is better shown in line 5. That's what happens under the surface. There's a danger here in C++ that you don't have these dangers in other languages which sort of use range checking. As a reminder, C++ doesn't use it for reasons of performance. If you're going to check to see if you're always within the bounds of an array, you have to put those tests in. It slows it down. You get safety at the expense of speed, because C++ was created at a time, C as well, where speed was paramount. There was no opportunities, if you like, spare CPU cycles to put in these checks. Does lead to danger. So if you look at the example at the bottom, here we're creating, we have some int, it already exists, and we're creating a pointer to that. So ptrint points to the address of some int. Lines 2 and 3 are valid. They're fine. They'll work. So we could take our pointer to an int. We could add on 3. So I'm jumping 3 integers ahead. I don't have a clue to what I'm pointing to, because this isn't an array, one presumes. And then dereferencing it. So that's a silly, fundamentally dangerous thing to do. I'm just jumping to a piece of memory without necessarily any guarantee what's there. And line 3, I can also do that. So I can take my pointer to an integer and view it effectively as an array. I can view it in exactly the same way as an array. So line 3, I can type in, I can code as equivalent to line 2. I can view my pointer as the start of an array, and I can then say array index 3. And because the two things are equivalent, line 2 is what gets to be executed. So I can take any integer pointer and treat it, consider it as if it is an array. Now, obviously, it's silly to do this, but the language permits you to have that freedom, that flexibility. So it comes into, I suppose, the takeaway on this here, that an array name and a pointer can be mostly used interchangeably. Where you have one, you can use the other. And the reason for that is that whilst arrays are convenient constructs for us to think about how we're arranging data, in terms of how they get to be implemented and how things get to be looked up, we're fundamentally doing pointer arithmetic at the start of it, indexing it by a certain amount and then dereferencing it. That's how arrays work under the surface. Just so happens to be that in C++ it's all visible and interchangeable. So arrays are, in essence, pointer. Pointer arithmetic is how you get an array. But not all pointers are arrays. That's the counterpoint where C++ lets you treat them as if they are, but we need to be cautious in doing that. Constant pointers is the next thing we want to have a look at in our survey of different miscellaneous aspects for pointers. This ties into the use of the const keyword. So const keyword, C++, lets us specify that something should be read-only. It should not be changeable. We can read it, but we can't change it. There's different ways we can use this with pointers. You can see the 4 different types here. Over on the left-hand side, the most flexible one, a non-constant pointer to non-constant data. So we have a pointer, we can change the thing that we point to, we can jump about memory, and we're also allowed to change the value of the thing that we point to. We can change memory itself. A non-constant pointer to constant data. In this case, we're allowed to change the thing that we point to, but we're only allowed to read it. We're not allowed to actually change the byte values themselves. So we can look about memory, but don't change any of the values of memory themselves. Constant pointer to non-constant data. We must always point to the same location within memory, and we're allowed to change the bytes of that location. And constant pointer to constant data. In this case, we must always point to the same location, and we're not allowed to change the bytes, just read only for that fixed location. So useful things to put in terms of how they're implemented. It's okay, it's a little bit of an elegance, I suppose. If you want to have a non-constant pointer to constant data, you have it over here. So for example, we've got an int data, set a value to 10. We're creating a const int pointer equal to the address of data. So in that particular case, the data is viewed as being constant. We're not allowed to change the thing we point to. And as a little aside there, notice in line 1, int was declared not to be constant. But in line 2, we're introducing an additional restriction on our pointer that, yeah, we can access it, but we're not allowed to change it. That's perfectly fine. A constant pointer to non-constant data. So in this case, the thing we point to must always be the same. We're not allowed to change the location in memory, but we're allowed to rewrite the bytes of what we're pointing to. To do this, you can see the middle example, or the box in the middle of the screen, where the const then moves to the other side of our integer pointer. And the final one, which looks a bit cumbersome, is a constant pointer to constant data, if you need that. So again, line 2 at the very bottom is constant pointer const. So we have to use it twice to signify the pointer being constant and the thing that we point to also being constant as well. It's a good idea to use these things, and these tie into what's known as the principle of least privilege. What this means is that if you are writing a method which needs access to a struct, a class, some other object, you should construct the method so that in terms of the parameters, the things that are passed in, they're passed in with just sufficient privileges, just the privileges that you need, but no more than that. So if I want access to a record to process it, and I know that this method will only ever read the data, will never change it, then in terms of the parameter that passes that in, I should set it to be a const parameter. I should say that this method accepts in a const parameter, highlighting to everybody and also enforcing within the method that I won't inadvertently change it, and I'm broadcasting to other people, you can call this here, and I'm indicating I won't actually change the thing, so it's just read only. Very, very good thing to put in. It's safe, it helps communicate to other people what the code does. And that's where const really should be used, and we should all get into the habit of doing that as often as possible. So const is often encountered when passing pointers as function arguments. Set it up so that the pointer has the right amount of freedom, the necessary, but no more than that. So helps protect against functions inadvertently changing data. It's safer. Also entails that both the const and non-const arguments can be passed into the function, so it makes it more open and flexible to the callers as well, and also lets them know a little bit more about what that method is going to do or likely to do. A little here about casting of pointers. So pointer, it's just a memory address, so we need to have the thing that we're pointing to that tells us how to interpret and the number of bytes we need to interpret at that particular address. We can turn one pointer into another type of pointer, and here we're thinking about the casts that came in with C++11, the ones that we should be using, as opposed to the old style C++98 cast, which let you change it without any questions being asked. So static cast is a good one to use. It's going to let you at compile time. So static means at compile time it will try to do the conversion. So for example, lines 1, 2, and 3 down here, we're getting a circle. We're getting a pointer to a circle in line 1, and we're assuming we've got an inheritance relationship that a circle is a type of shape. So circles is a more refined class. In line 2, there we're creating a pointer to a shape, and we're passing in, or in creating the pointer to the shape, we're starting off the pointer to a circle, and we're using our static cast then to cast that into a shape. So we're passing that into a shape. It'll be checked at compile time. It'll work out, okay, so shape is a superclass then of the circle one. That's a permissible extension. We can treat all circles as if they are shapes through the inheritance relationship. So I'll let you do it. It'll compile. In line 3, if we try to cast it to something that presumably we're not able to cast it to, so for example, taking a circle and turning it into an int, there are some rules. You arguably could put in a constructor to let this happen, but let's assume that there's no normal way of doing this. There our static cast would fail at runtime and would say, well, I don't know how to convert a circle into an integer, so I'm not going to go ahead with the compilation. Dynamic cast, which we'll look at a bit more when we look at objects. This is a runtime, so it's actually tested at runtime, so it runs a bit slower because we've got to do those checks there, but it's more flexible. So if you're casting up and down inheritance hierarchy, so if I have a pointer to a shape, but I know that it's really a circle, and I want it to treat it as if it is a circle, then I'd be using a dynamic cast at runtime just to verify that that is indeed the case, and then carrying on. Other aspect, so a pointer points to a location in memory. Normally we think of pointing to data, but our machine instructions, our methods, our functions are defined as sequences of bytes containing instructions that ultimately will be executed on the processor. So you can also have a pointer to a function, and it's actually quite useful. So this means that we can call another method and we can pass into it a function pointer. So it is an address in memory of a piece of code that can be executed, that can be invoked. And that lets us then have a lot of flexibility in terms of particularly, for example, things like sorting, where you may have two objects, you want to have a method that will enable you to work out which object is bigger or smaller than the other, and you can pass in the pointer to a function that will actually do that, and it can then be made bespoke to the different objects that are being passed in. You can see an example of what a pointer function looks like down at the bottom. So we've got a return type, it's our char pointer. We've got three parameters that have been passed in, the int, the char pointer, and the int. And as opposed to having a method name, here we have a pointer to some function in memory. So it is the address in memory where that function actually resides and exists. And we can pass these things in as arguments and otherwise manipulate and invoke them. So it's quite flexible, quite powerful. Smart pointers are something that are really important. In languages like Java, how they work is effectively using smart pointers under the scenes. Now, we're going to do compare and contrast. We've got a smart pointer and a raw pointer. A raw pointer is just simply an address, something that points to an address in memory, and that's it. If you like, it's almost equivalent to primitive data. Smart pointers are smarter, they're richer, they're more sophisticated, they're almost inclined to sort of classes. And smart pointers, the reason they're called smart is that they will manage and do a number of things. So you can set a smart pointer up that says that, okay, I want you to point to something. If ever you go out of scope, so you're going to be deleted, delete the thing you point to as well. You also can have reference counting smart pointers that if you have an object and you have multiple pointers pointing to it, they will know amongst themselves how many other objects point to this one. And if the last one it points to it gets to be deleted, goes out of scope, then it'll clean up the thing that it points to as well. So these are great things by way of avoiding memory leaks within our programs. And C++11 recommended advice is you do use them if you're programming, and you most certainly should. If you want to write them, effectively it is a class. You're overloading things like the arrow operator, the dereferencing operator, and you're putting in a bit of additional functionality in terms of working out what is your link to. If you ever destruct it, then taking appropriate action based on that. There's a couple of built-in ones in the C++ standard library. Unique pointer and shared pointer. Now, these are actually nice things because if you're using them, you can decide what type of smart pointer is appropriate. And there are some forms. You've got a sort of a quick and easy smart pointer, and you've one that has more, it's a bit slower to use than other ones. Languages like Java and so on, you basically don't have the same degree of control over it. So C++ exposes all of these things to you and lets us as the programmer decide what's optimal. Now, if performance isn't paramount to you, this can be a necessary welcome, but if it is paramount, it's good to have this degree of choice. So unique pointer, uniquely refers to an item, and if the pointer goes out of scope, that item goes out of scope. So it's one pointer to one object. A shared pointer is basically our reference counter pointing, where we can have one object and multiple different things pointing to it. And as long as we have at least one thing pointing to it, we keep it in, we don't delete the object. But whenever the last one goes out of scope, then we also remove the object as well. And you see an example of using a raw pointer over on the right hand side, where in line 3 we're creating some class to it, make sure we have a pointer to it, and then line 5 we better make sure we remember to delete it having created the thing. For a smart pointer, we can just create a smart pointer straight to it, and goes out of scope, we don't care, the smart pointer will delete it for us. References then, quite closely related to pointers. Reference is an alias for another variable. Modifying the reference changes the value to which it refers, so it's similar-ish to a pointer. Reference variables must be assigned as soon as they're created. So an example over here, where in line 1 we're creating an int called val. In line 2 we're creating a reference. So we're using the ampersand character as a way of signifying this is a reference. So effectively, reference to val and val are the same thing. So val is the actual piece of primitive data, and reference to val is just another way of referring to it. We can add 2 to reference to val, which is the same as then adding 2 to val itself. Line 3 is not permissible. If you are creating a reference, you must, at the point of definition, link it to the thing that it's being referenced for. What's the difference between a pointer and a reference? Not a lot. You can think of a reference basically as a named constant for a given address. So more or less a non-null const pointer. It can never be null. It must always point to the same thing, but you're allowed to change the thing that you point to. References are automatically dereferenced. So if we have a pointer, we have to put in the asterisk to dereference the thing, and it's something the programmer has to do. If we're using a reference, it's done automatically for us. We just use the reference, and that's an automatic side effect of it. So it makes them a bit cleaner, a bit easier to use. So functionally, references and pointers, they're the same type of thing. They're both ways of referring to the same one. References look a bit cleaner, maybe a little bit easier to understand, a little bit safer to use. So there are good reasons why you might want to do it. And if you have a choice between using a reference or a pointer to something, use a reference to it. It's just going to be cleaner, safer code overall. The only situations where we can't do this is if we are dynamically allocating memory, but we will get given a pointer and address in memory. So there will be some cases where we can't avoid the use of pointers. Key takeaways at the end of this, bit of a mixed bag. Pointers, they're powerful, they really are powerful. They give you a lot of low-level control. as a programmer, we can choose what we want to do, and C++ gives us the freedom to do that. To provide a flexible means of manipulating data stored in memory. And a lot of fancy high performance things will look at more efficiently moving about memory. Although with great power comes great responsibility. You can mess things up badly with pointers. We have to be extra careful when we're using them to make sure that we don't step outside our bounds. We don't inadvertently change something we weren't intending to do so. And the usual thing at the bottom, to reiterate the one from the last talk, to help us there, we need to be quite careful in creating code where it's clear to somebody reading it, or future selves or somebody else, what the purpose of the thing is. And some of the arrow operator or references or things come in to help us make code a little bit clearer in terms of the expressions. That's all we want to look at in terms of pointers. Bit of a mixed bag, but it is a useful feature of C++ really to delve into and get a good amount of exposure and experience with.